going to start a new chapter. And this chapter is actually atypical organic chemistry chapter because we're not talking about any reactions pretty much. And it's a chapter about the spectroscopy. But that doesn't mean that's not important. Actually, this probably is the most important chapter in this semester because the content, the topics covered this chapter will be, we're going to review them again and again and again many times in all the remaining chapters, pretty much. So all the remaining chapter will be a section about the spectroscopy of the class of compound you will be learning in that chapter. So this is the foundation of those parts. So please put effort into. Okay. So right now in organic you probably know that in this semester there's almost half semester you will be doing unknowns. So basically you need to do a lot of reactions systematically to figure out what kind of unknown compound you might have received. Okay. And and that is actually how chemical structures were determined in the early days, that's before 1950. Almost all chemical structures were determined that way. Just pretty much follow the same method you will be doing in the later part of this semester in the lab. Okay. But since the 1950s, the use of the electromagnetic radiation to determine structure become more and more common because it's the saves a lot of time, faster, and actually can give you structure in basically you will be more confident about the structure, and you probably get more information about the structure. Under the study of how a compound responds to electromagnetic radiation, or in a simple term called light, is called a spectroscopy. That's just the terminology. Okay? So we will be learning the three types of spectroscopy methods in this chapter. The first one is the most important one in chemistry, called nuclear magnetic resonance spectroscopy, also in short called NMR. Okay? That's the most important, the spectroscopy technique for chemists. The second one is called infrared spectroscopy. It's also pretty important. Let's say our weight as second important one in this chapter. And UV visible spectroscopy, it's not hugely important in organic chemistry, but it's pretty important in analytical chemistry for quantitative determination. It's actually very important. You guys probably have done something in the as early as 127. Did you guys do that? 127? Absorption spectroscopy of nickel complexes, something like that? Yeah, I probably have done that. And when we also going to learn mass spectrometry, technically it's not a spectroscopy method, but it's also an instrumentation method that gives us information about the molecule, mostly determining the molecular mass. So we're going to learn them together with all the three spectroscopy methods. So the importance, pretty much, this is the most important. This is second, and the UV and the mass, probably they are similar. So let's first look at some general principle of molecular spectroscopy. The first thing is that we have to learn, what is the nature of electromagnetic radiation. So this you probably learned in general chemistry already, maybe, or you probably learned in high school. Then you repeated in general chemistry. Now I just briefly go through again. So electromagnetic radiation, also called light, can be described as an oscillating wave of electromagnetic radiation or a series of particles called photons. So this interesting property called particle wave duality, and this particle wave duality actually is not limited to electromagnetic radiations. Technically, even all of us has a particle wave duality. Just the particle wave duality is, it's more obvious for those, for electromagnetic radiation. For us, the wave property is too, too weak to be to show its influence. Okay, but for electromagnetic radiation, you do need to consider both wave particle property in order for you to deal with the problems or use the electromagnetic radiation. So if you apply the if you consider light consists of a stream of particles called photons, then the energy inside each photon is equal to Planck's constant times its frequency. So this is a most important equation in this chapter probably. The energy inside each photon is equal to Planck constant. This constant times the frequency of this photon. Okay? Under this Planck constant. Okay? Under also the light or electromagnetic radiation always travels at the speed of light, which is related to the frequency and the wavelength. Speed of light is equal to frequency times the wavelength. Because the speed is fixed, so the frequency is inversely proportional to wavelength. That means under the energy of a photon is proportional to frequency. So the energy of inside each photon is inversely proportional to the wavelength. So the longer wavelength it is, the less energetic the photon is going to be. And the energies of the the light span a huge range. So if you look at the frequency of those photons, can go to as far as the 10 to the 20th order of hertz. Hertz is basically one repetition per second called 1 hertz. Okay, so the frequency could be as high as 10 to the 20th order of magnitude. 10 to the 20th. Okay, in terms of a high frequency end, and a lower frequency end can be as low as 10 to the 4th order. So the frequency span the 16 orders of magnitude. And the wavelength you can calculate basically could be as short as 0.0 something angstrom or 0.00 something nanometer to about the 10 to 12 nanometer. That means about a kilometer range. Okay, so that's the long wave the radio frequency, long wave radio wave. So those fleets before the satellite was available, those fleets on the ocean, when they want to commute with the base, they have to using those very long wave radio. Now with satellite, the story may be different. They can talk to a satellite, then beam to the another part of the Earth, maybe doable. In the older days, without satellite, they have to use long wave radio. The frequency actually kilometer long. So now the kind of electromagnetic radiation interest to us is mostly about this for NMR. So it's a high frequency radio, the high frequency radio wave. Okay, and the infrared, you can guess, is around here, just infrared. UV visible is somewhere here. Okay, and also just not really directly related to this course. And you all know you are using cellular phones, and the cellular phones, they are using the frequency of microwave range. Okay? And you must heard of like 5G things. This is the current most advanced cellular the network is basically the high frequency microwave. So the higher frequency, the carrier wave, you have more bandwidth. Okay, so the 5G one, you can have like close 1,000 megabits, per second bandwidth. But usually the higher the frequency, the shorter the range. And so 5G, coverage is not very useful in rural area because those carrier cannot afford to put so many base stations in a rural area because lack of users. Okay. Anyway, so that's basically the electromagnetic the spectrum. So basically the NMR is a lower energy end. Infrared is a bit higher energy than the NMR, and the visible and the UV they are of even higher energy than the the infrared. So next thing is the principle of molecular spectroscopy. So when you look at the a molecule, one important aspect of a molecule is about its energy. And then if you consider the energy of a molecule, you really cannot take any random energy value. Okay, so the quantum mechanics dictates that the energy of a molecule, the must in such a way that they are in the certain energy levels. They are separate one another by some finite amount. So we say energy is quantized or discrete. So molecules only can take certain fixed energy levels. Okay, not like I can take anywhere. For any given molecule, only can take certain fixed energy levels. Okay, so the just like you consider, molecules are climbing ladders. Okay, basically in a sense, only can put a certain energy level. Then, if if a molecule change energy level, for instance, a molecule originally at energy level 1, okay, then if you want to go to a higher energy level, say E2, those are well-defined energy levels. So the E2 energy is a higher energy than E1. So the energy cannot be randomly generated from nothing. Okay, so energy must be provided into this molecule. So basically what kind of energy need to provide must equal to energy difference between E2 minus E1. So this energy difference must be provided to the molecule in order for the molecule from E1 to E2. Then the most common way to provide this energy is using a photon of just the right amount of energy, h nu. Okay, this h nu equal to delta E. If you let such a photon interact with this molecule, then the molecule will go from E1 jump to E2, and the photon is absorbed. Okay, so this is the most common way to explain, the absorption of a photon. And you can use this absorption in another way. So if you see that a molecule is able to absorb a photon with this frequency, okay, that immediately tell you that this molecule, okay, must, has two energy levels that are separated by this amount of energy. So if a molecule is absorb a photon with frequency nu, h nu, okay, that is called nu, okay, frequency, okay, then we know the energy inside this photon is h nu. That's energy inside of the photon is absorbed by this molecule. Okay, that means the fact this molecule absorbs this photon means this molecule must have two energy levels, E1 and E2, and the difference between these two energy levels, delta E, must equal to h nu. So that's the general principle of molecular spectroscopy. And the most common way of such a, the result of this absorption most commonly is plotted as this x-axis usually is either the frequency or wavelength of the photon, and the y-axis is absorption or the absorbance most likely. Okay, is a quantitative absorption, basically measures how much light is absorbed. Okay, so this is the most common spectroscopy. So let's say, you're gonna say, oh, so this is usually we use this peak. Okay, is what frequency photon is absorbed. Okay, then I know that my molecule must have two energy levels. These two energy levels is separated by the energy equal to this. The frequency is read from here. Okay, so that's the information we learn from general molecular spectroscopy. Now, how we can make use of this information? Let's first look at the called NMR spectroscopy. So the the NMR, as named such as called nuclear magnetic resonance. Okay, so let's first look at how the individual nucleus look like. Okay, so when we say nucleus, a nucleus means we don't care about for the time being, we don't care about the electrons around the nucleus. So in most of the cases, we're dealing with molecules and atoms, right? And an atom is basically separate two parts. One is the nucleus and outside electrons. Okay, and as we all know, the nucleus must be positive charge. Okay, and the electrons are negative charge. And the thing is that each nucleus you can consider is a positive charged sphere. Okay, but they don't stay there just just motionless. Okay, each nucleus always spinning, just like electrons. It will be spinning. Okay, and this spinning nucleus, if you learn from physics, anyone never learned physics here? Okay, at least learn some physics. So if you recall once you have a spinning charge, you know how the electromagnet work, right? You basically have a coil, okay? A coil inside you have let's say the simplest electromagnet you have the iron there. Then you wrap coil around it, then pass electric current through the coil. Then you can create a weak electromagnet. Okay, but the key part is if you have the current go through circular pathway, it can create a magnetic field. That's the key part. Now you have the a sphere spinning is very similar to have electric current going circular pathway. Okay, because they are spinning, charged, spinning. So this spinning nucleus will create a magnetic field perpendicular to the direction of spinning. So if the spin like this, then the magnetic field will go north or south, and the direction is not relevant. Okay, so but this spinning will create a magnetic field perpendicular along the spinning axis. Okay, do you see the picture here? This spinning nucleus create a magnetic field parallel to the spinning axis. Okay, and each spinning nucleus behave like a small magnet. Its orientation is random. Okay, could be any direction. Okay. Now, if you place those spinning, the nuclei into powerful magnetic field. Okay, so then those this is before putting a magnetic field. If you putting those nuclei into magnetic field, you know those small magnets, they will interact with magnetic field. So the some of them, okay, like those red ones, okay, they will be assume the magnetic field is going up, like this arrow shows going up. So those some of the small magnets will be parallel to the magnetic field, and the some of the small magnets will be anti-parallel to the magnetic field. And if you play with the magnets, you will know that only under those two situations, there will be no torque on those, you know, the spinning, the small magnets. Anything other than parallel, anti-parallel will be torque, okay, will be rotating. Only on those two situations, it will not be rotating. Okay? And also, if you ever played with two magnets, you know that this situation is a bit more stable than this situation. Means that the small magnets parallel to the bigger magnets, the one. This situation, the red one, okay, will be more stable than the green ones. Okay. Parallel, big magnets want to align the small magnet in the same direction as it, as itself, right? This big magnet, okay, big magnetic field will align the small one in the same direction as itself, okay? So that's create two states. A less stable state, the green one, under the red ones, okay? And obviously, these two states will be related to the strength of magnetic field. This one, this bigger one, okay? If the stronger the field it is, the difference of energy in these two states will become greater. Because this purely depends on magnetic field. The field is, no, the small magnets, they have a fixed field because it's purely based on what's spinning, okay? Under the big magnets, this one, green one, the stronger it is, the interaction will be stronger. So you will see greater energy difference between the, the more stable one, okay? This was the more stable one and the less stable one. Okay? So now you're see before the magnetic field, the two states have, the two kind of, all the nuclei have the same stability. When put into magnetic field, because the interaction between the external field and the weak field created by spinning, the nuclei, now you're having two different states, okay? And the energy difference between these two states is proportional to external field strength, okay? And now, because you have the two states, okay, you have a energy difference between the two states. If you introduce electron, magnetic radiation, the if you introduce electromagnetic radiation, frequency is nu, okay? If the h nu equal to delta E, then those nuclei at a lower energy state can undergo a transition to a high energy state, and that the photon will be absorbed. Okay, so that's why we call it nuclear magnetic resonance, because you need first this because of spinning nuclei create small magnets, and you need external magnetic field to create the two states. Under these two states, energy difference is directly proportional to external magnetic field. This is important, directly proportional to external magnetic field. If the external magnetic field B0 becomes stronger, the energy difference between these two states become greater. And then the photo frequency photon frequency that's needed to promote, you know, the nuclei go from low energy state to higher energy state, also frequency become higher. So this kind of absorption photon we call nuclear magnetic resonance. We say the resonance happens when a photon with this frequency delta E equal to h nu is absorbed by this nuclear magnetic system. We say a nuclear magnetic resonance happens. Okay? And basically this frequency will able to tell us the magnetic field, okay? You know, the of the nuclei is experiencing. So the real NMR spectrometer, you always need you know a very powerful magnet, okay, to generate, you know, the magnetic field. So the stronger the field is, the, you know, the better the instrument is. And the thing is that, you know, even for you know the middle range instrument, you will need a magnetic field several, you know, more than several Tesla, probably at least 10 Tesla. Magnetic field unit is called Tesla, not the electric car, you know, but the same origin, I guess, you know, when Elon Musk, you know, invented Tesla, probably is just, you know, to honor that Tesla, same Tesla, you know, this magnetic field strength is going after, you know, but you need generally you need at least 10 Tesla. And this is actually a very, very, very strong magnetic field. It cannot be achieved by any permanent magnetic field I know of. Okay. Also, you know, cannot be generated by conventional electromagnetic field, because if you you know if you use conventional electromagnet to generate such a strong field, you need a current is so high, the coil will be melt down. Okay? So basically, if you want such a strong magnet, you have to use an electric coil without resistance. And what kind of coil that can be? If electric coil without resistance, and if it's an electric coil without resistance, what kind of coil we call? Any conventional conductor, you have resistance, electric resistance, but electric coil without resistance, a conductor without electric resistance, called what? Anyone? A conductor without electric resistance? Nobody knows? Superconducting. Okay, it has called superconducting. Okay, so all those modern magnetic field require superconducting coil. The superconducting coil, as far as current state art, still need liquid helium. Liquid helium is very expensive. That's why running modern NMR instrument actually pretty expensive. But anyway, you need a powerful magnet, and you need a radio frequency transmitter to apply radio wave to the sample, and a detector for detecting emit or transmit a radio wave. So that's the major component of instrument, but I'm not going to tell you details because that's you know, we'll mostly talk about how to understand NMR spectrum. So now in chemistry, the most kind of nuclei we will be dealing with is what kind of nuclei? Let's say in chemistry, what kind of elements we are most commonly dealing with? In chemistry, organic chemistry, let's put it this way. Organic chemistry, what kind of elements most commonly we use? Carbon, obviously, and hydrogen. Okay. So now is something I don't want to go to detail to explain. You know for the normal NMR, you know spectroscopy, we only it's convenient for us to deal certain kind of nuclei because hydrogen, there's a few isotopes. We know hydrogen 1, hydrogen 2, hydrogen 3. Hydrogen 1, hydrogen 2, they are stable, not radioactive. Okay, and the carbon, the major isotope is carbon 12, and the carbon 13 is a minor isotope. And but just for the reason I don't want to go to detail, it's convenient to deal with carbon 13 and hydrogen 1. Okay, and hydrogen 1 is actually it's the major isotope. More than 99% of nature occurring hydrogen and hydrogen 1. So that's the reason why hydrogen 1 we also call a proton is the most common most common the nuclei we're going to deal with in organic chemistry. The second most common nuclei we're going to be dealing with in organic chemistry is carbon 13, and we're going to talk about later. But let's first look at the hydrogen 1. Okay. So all the discussion we have had so far applies to hydrogen 1, or we call proton. Proton is basically referred to the hydrogen isotope. We only have a single proton inside, no neutrons. Okay, that's the major isotope of hydrogen. And the key part is if we look at the resonance frequency, then only can tell us the magnetic field the nuclei, the nucleus is experiencing is not superly useful. Okay? Because in that case, if that's the case, then all protons going to have exactly the same, the resonance frequency. Resonance frequency means the frequency of a photon absorbed by the photon, by the proton, if the magnetic field strength is the same. Okay? It's not very useful. But so far, okay, we only discuss about the nucleus yet. I'm just talking about nucleus. Okay? But in real world, when we deal with organic compound, those hydrogen atoms, okay, besides the nucleus itself, they must also have electrons around it. On the over 99.9% of cases, only on a very rare case, the hydrogen atom only exists as an electron-free proton, the nucleus, no electron whatever. Okay, that's very extreme cases. Means just a very strong acid. You can see the proton, the nucleus. Oh, I don't have any electrons around it. Okay. In 90.99% of cases, the proton, the nucleus, always have electrons around it. That's the key part, okay? Because electrons, they also respond to magnetic field. So the key information the proton and the Mach can tell us is actually about electrons around the proton. And as we know, all the proton nucleus, they must bond it. Almost all of them, they are bonded to something else. Bound to something else means always electron around it. Okay? So the chemistry is all about electrons. Okay? So if you know a lot about electrons, yes, you can tell a lot about the information of the proton. Okay? So the thing is the electrons also respond to magnetic field in the form of circulation. So the means if the electrons, in a standalone hydrogen atom, electrons may move randomly more or less around the nucleus, but once they place in the magnetic field, the movement become well defined in a sense. Okay, so now exact movement of electrons, basically when you have electrons, you put a magnetic field, you always will from random motion becomes circulation. Okay, then the circulation direction it depends on the property of the molecule. So generally, when you look at the magnetic property of molecules, there are a few types. Diamagnetic molecule. What kind of molecule is diamagnetic? In general chemistry, do you know what kind of molecules are paramagnetic? Rosa Amanda, Amanda Rosa, we have. So it's not here, okay. Matthew Verodi, also not here. Valerie Yakushiva.
I'm not sure though.
Oh, okay. So yes.
Is it when on the orbital diamagnetic is 2 electrons and paramagnetic is 1?
Kind of, okay. So if you look in general chemistry, if a molecule with unpaired electrons and non-zero unpaired electrons, they are paramagnetic. Doesn't matter 1, 2, 3. Have non-zero number of unpaired electrons, they are paramagnetic. Okay, but the most of organic molecules we are dealing with, all electrons are paired. Okay, and if they are paired, they're diamagnetic. So the difference between paramagnetic and diamagnetic is the paramagnetic one will be attracted by magnetic field. Okay, diamagnetic will be slightly repelled by magnetic field. Okay, slightly repelled. So that's the key point. Okay, so because the organic molecule we're dealing with almost always diamagnetic. Okay, just for the sake of simplicity, we can consider all organic molecules we're going to be dealing with in NMR, they are diamagnetic, just for the sake of simplicity, okay? Then, in diamagnetic molecules, the circulation of electrons always create a field that's against external field. That's why it's diamagnetic. If the magnetic field go this way, right? Electrons circulating generate field against it. So that's how you create the slight repulsion force. Okay. Now that's important to keep in mind. Okay. So think about it. Look at this hydrogen atom. Okay. Where's my? Okay, here. Look at this hydrogen atom. Now it's not isolated hydrogen nucleus. It's a hydrogen atom. In addition to the nucleus, have electrons around it. Okay? So those electrons around it will be undergoing a circulation, okay, induced by this magnetic field. And this magnetic field will, this circulation will induce a field against it. So, assume the big magnetic field, okay, is going up, okay, going up. So this is a hydrogen nucleus. So then the circulation of electrons will create a field against it. Okay. So net effect is because of existence of electrons, the field, magnetic field experienced by this nucleus will be a bit weaker than the original one. This we write this equation. Effective field experienced by the nucleus is original external field minus the field is formed by circulation of electrons, and this makes field a bit weaker. We say the electrons will be shielding the protons from the external field. Okay,